Welcome, developers and AI architects. Today, we are moving beyond single-threaded development. We're going to explore multi-agent coding workflows, learning how to coordinate multiple Claude agents to work on different branches of a project simultaneously. Let's get started. Let's begin by defining multi-agent coding workflows. What exactly are they? They represent the orchestration of multiple autonomous AI instances operating concurrently on your project. The basics are straightforward. Instead of waiting for one Claude session to build your database, then your API, and finally your UI, you deploy multiple agents to tackle these simultaneously. Why is this revolutionary? Because it eliminates sequential bottlenecks and prevents context window bloat, drastically accelerating your software delivery. How do we achieve this? We utilize multiple terminal sessions, specialized subagents, or Claude's native agent teams. In our deep dive, we recognize that this requires a mindset shift. You are no longer just a programmer. You are a technical manager orchestrating a swarm of AI developers, defining boundaries, and synthesizing their final deliverables. This flowchart highlights the contrast between sequential and parallel development. On the top path, a single agent processes task 1, then task 2, and then task 3, causing a bottleneck. On the bottom path, the developer delegates the work to a multi-agent parallel architecture. Agent 1 handles the database, Agent 2 handles the API, and Agent 3 builds the UI simultaneously. These independent threads converge perfectly into the merged application. To successfully run multiple agents, we must enforce isolation. This brings us to Git work trees. What are they? They're a Git feature that allows multiple working directories to be attached to one repository. The basics: they give each agent its own sandbox. Why is this absolutely critical? If you have two Claude instances sharing the same directory, their file edits will collide, resulting in corrupted code and Git conflicts. How do we solve this? Claude Code has native support for this. By simply running Claude W followed by your branch name, Claude automatically provisions an isolated environment. Looking at the deep dive, this physical separation on your file system is the ultimate safety net. It guarantees that an agent aggressively refactoring your backend API will never accidentally overwrite or break the live code your frontend agent is currently testing. This architecture diagram maps out physical isolation. At the top sits your main Git repository. It branches out into distinct physical directories: your main worktree where your IDE lives, worktree 2 for the auth feature, and worktree 3 for the UI feature. Claude Instance A and Claude Instance B operate entirely within their respective blue sandboxes. They can compile, test, and break code locally without ever impacting each other or your main environment. Beyond manual work trees, Claude Code offers native orchestration, agent teams, and subagents. What is the difference? Subagents are isolated workers that report only to the main agent. Agent teams, however, communicate peer-to-peer and share a central task list. The basics are simple. You choose the pattern based on communication needs. Why does this matter? If you just need isolated research, use a subagent. But if you have complex work requiring discussion like a security reviewer validating a coder's logic, you need an agent team. How do you start? You enable the experimental environment variable and simply ask Claude to create a team. For our deep dive, realize that agent teams operate as a true swarm. The team lead dynamically spawns teammates. Crucially, these teammates use a send message tool to chat with one another, coordinating task dependencies completely autonomously. This diagram contrasts the two native coordination patterns. On the left, the subagent pattern shows a strict hierarchy. Subagents 1 and 2 only communicate vertically with the main agent. On the right, the agent team pattern reveals a swarm architecture. The team lead spawns the agents, but teammate A and teammate B communicate horizontally via direct messaging. They both interact with a shared task board, enabling true autonomous collaboration. When multiple agents work independently, we face a major challenge: maintaining consistency. This is solved through context engineering for parallel agents. What does this mean? It means ensuring all agents follow the exact same rules without having to talk to each other. The basics involve leveraging Claude.md and specification files. Why is this critical? Because if you have one agent writing React components with Tailwind and another using CSS modules, their code will be incompatible when merged. How do we align them? We place our strict rules in the root Claude.md file. Looking at the deep dive, because every isolated Git work tree shares the root repository history, every single Claude instance automatically loads this file at startup. This guarantees that an agent spawned in a completely fresh terminal instantly inherits your organization's exact architectural guidelines. This sequence diagram maps the flow of shared context. The global repository holds the Claude.md file. When Agent A and Agent B are spawned, they both automatically load the exact same tech stack and rules. Agent A implements the backend, and Agent B implements the front end. Because they were grounded in the same architectural reality from millisecond zero, when they push their branches back to the repository, the code merges seamlessly. Let's explore an advanced orchestration technique, the infinite agentic loop pattern. What is this? It's the use of metaprompting to dynamically spawn multiple agents from a single command. The basics involve a high-order prompt, which is a prompt designed to write other prompts. Why is this powerful? Imagine you need a new dashboard layout. Instead of generating one design and tweaking it, you can command Claude to generate 5 distinct variations simultaneously. How? You define a custom /command that accepts your spec file, an output directory, and a worker count. Our deep dive reveals the brilliance of this pattern. The lead agent actively scans the output directory to see what has already been built. It then formulates unique, non-overlapping system prompts for each subagent, guaranteeing diverse, high-quality iterations without redundant effort. Here we see the execution flow of a high-order prompt. The user triggers the custom/command. The lead agent reads the specification and performs directory reconnaissance to understand the current state. It reaches the metaprompt generation node, where it intelligently crafts 3 unique prompts. These prompts spawn subagents A, B, and C simultaneously. Each explores a different architectural path, ultimately saving their distinct, highly valuable artifacts back to the output directory. Safety is paramount in automation. Slide 6 covers tool restriction and safe parallelism. What does this mean? It means applying the principle of least privilege to your AI agents. The basics require giving each specialized agent only the exact tools it needs. Why must we do this? In a highly automated swarm, an ambitious agent tasked with writing tests might decide to fix a core routing file that another agent is currently actively modifying, causing widespread corruption. How do we prevent this? By defining your agents in Markdown files and strictly setting the allowed tools parameter. As shown in the sample code, you can allow an agent to run tests, but explicitly revoke its write access. In our deep dive, tool restriction acts as an architectural firewall. By granting specific tools like WebFetch for your UI agent and SQL Bash access for your database agent, you guarantee they stay strictly in their lanes. This state diagram illustrates role-based tool access. When an agent is spawned, it adopts a defined role. The front-end developer role transitions to allowed write access, but if it attempts to touch the database via Bash, the action is hard-blocked by the system. Conversely, the QA code reviewer is granted full read access, but any attempt to execute a write command is blocked. This guarantees execution safety across your entire project. Let's apply these concepts to a real-time use case, the feature pivot. The scenario: your startup must overhaul the checkout UI while simultaneously migrating the backend payment database schema. The challenge: doing this sequentially takes days. Doing it concurrently usually breaks the API contract. Here is the flawless execution. You spawn Agent 1 locally using a Git worktree for the UI. You give it the API spec.md file and tell it to build the React components. Simultaneously, you spawn Agent 2 as a remote cloud background agent, give it the same spec file, and tell it to write the PostgreSQL migration. The outcome: Agent 1 builds the UI, and Agent 2 builds the database. Because they were both anchored by the exact same specification file, their independent branches merge flawlessly. A multi-day sequential sprint is completed in 30 minutes of parallel AI execution. Follow the journey of our parallel overhaul. In initialization, the developer creates the central API specification, then spawns the local UI worktree and the Cloud DB agent. We enter the parallel execution phase, where both agents write complex code simultaneously, without overlap. Finally, in convergence, the developer verifies the independent test suites and merges both branches to main, resulting in a deployment-ready application in record time. To wrap up, let's establish the best practices for multi-agent workflows. First, task independence. Never assign parallel agents to modify the exact same file. Always scope their tasks to distinct components. Second, enforce mandatory plan approval. For risky backend changes, use permission mode plan so the agent explicitly asks for human approval before executing code. Third, implement aggressive cleanup. Git work trees are amazing, but they consume disk space. Delete them once the branch is merged. Finally, monitor your costs. 10 parallel agents means 10 times the token burn. Start small and scale smartly. Thank you for joining this masterclass on multi-agent coding workflows. I invite you to like this video, subscribe, and visit quicktechie.com for premium certification prep, including massive Q&A banks, full ebooks, audiobooks, full-length training, and expert interview guides. See you in the next session. Our final mind map synthesizes your path to multi-agent mastery. You must establish isolation using Git work trees and role-based prompts. You drive orchestration by leveraging native agent teams and high-order meta prompts. You guarantee safety through strict tool restrictions and mandatory plan approvals. And your ultimate path to success, visiting quicktechie.com to unlock your full potential as a next-generation software architect.